Everyone. Today we'll learn about how to know whether there's ionic bonding between two atoms or covalent bonding. And also we'll learn how to draw simple Lewis dot structures. So first let's take a look at lithium fluoride. So that has lithium, which is a metal, and fluorine, which is a nonmetal. Those have very different electronegativities. Fluorine is much more electronegative than lithium, and so it will draw electrons towards it very much. Lithium has an electron configuration of 1s2, 2s1, and fluorine has an electron configuration of 1s2, 2s2, 2p5. We can represent the valence electrons around these atoms with Lewis dots. There is one electron here in the highest occupied principal energy level. There's one valence electron for lithium. And we can represent that using this one dot. Lithium is in group 1a. It will have one valence electron. And then fluorine, it will have, let's see, 5 electrons in the 2p, but also 2 electrons in the 2s, a total of 7 valence electrons. 7 electrons in the highest occupied principal energy level 2. So it will have 7 valence electrons and hence 7 dots. So I'm drawing them out here, spreading them out as much as I can. 2, 4, 6, 7. Another way to know that it would have 7 valence electrons is to see that fluorine is in group 7a. It will have 7 valence electrons. Yes, we said that there is a very different electronegativity between lithium and fluorine. Fluorine is so much more electronegative than lithium that it will pull electrons towards it much more than lithium does. And so this electron will not even be shared between the two, but will just pretty much just be given to fluorine. So that now we have lithium that's lost an electron and will have a positive charge. And now its electron configuration is 1s2. Previously it had 3 total electrons, and now it has 2 total electrons. Now this will make a lithium quite stable because now it will have the same electron configuration as helium, the most nearby noble gas. It will have a full valence shell. It will have just enough electrons to entirely fill principal energy level 1. And then fluorine will now have one more electron than it did before. Instead of ending in 1s2, 2s2, 2p5, it will now end in 1s2, 2s2, 2p6. It will have also a full valence shell. Principal energy level 2 is totally full. And also will have a negative charge because there's now one more electron than it used to have. This is lithium fluoride. This is going to be fairly stable because not only do both of these ions now have full valence shells, but also because there's going to now be an attraction between this positive and negative charge. This will be an ionic compound where it's just going to have a lot of lithiums surrounded by fluorides, and the fluorides will be surrounded by lithium, so that there can be just a lot of positive charges near negative charges. So this is an ionic compound. It's going to have a ionic bond. That is the attraction between those opposite charges. So this is a memorized thing. Ionic compounds are formed when you combine a metal and a non-metal. So let's try another case. What if we had N2? Is that an ionic compound, and does it have ionic bonding, or does it have covalent bonding, and is it a molecule? Well, you're starting with nitrogen and another nitrogen. They are nonmetals, and so they will not give and take electrons, but they will share electrons with each other. Each of these starts out as 1s2, 2s2, 2p3. Each of these starts out being in group 5a here. Each of these starts out with 5 valence electrons. And so they will each start out with 5 Lewis dots. So these are not yet stable. They want to have just as many electrons as the most nearby noble gas. They can become much more stable if their electron configuration ends in 2s2, 2p6. So they can do this by sharing electrons. Neither of these are more electronegative than the other. They're equal in electronegativity because they're the same element. And so there's no reason that electrons should go all the way to the right or all the way to the left. Instead, the electrons will be equally shared here. So this nitrogen has 5 valence electrons around it. And if this nitrogen can kind of contribute 3 more towards it, then this will soon have 8 valence electrons. And then this one currently has 5, and if the left nitrogen can contribute 3 more, then this one will soon have 8 around it as well. Each of these will soon have 2 more electrons in their principal energy levels. Sorry, actually 3 more electrons in their principal energy levels. Each of these, having electrons being shared, will now have 8 valence electrons around them. So you see how this nitrogen on the left has 2, 4, 6, 8 valence electrons around it. And this one also has 2, 4, 6, 8 valence electrons around it. These electrons in the middle can belong to the valence shells, the outermost principal energy levels, for both of these atoms. They're shared by both atoms. So this is very stabilizing. They both now have 8 valence electrons. They both have full octets. 8. So oct means 8. They have 8 valence electrons. This is one way to draw the structure that you have when nitrogen molecules are present. But much more commonly, we are going to represent each pair of electrons that are shared between those nitrogens with a line. Here, there are 1, 2, 3 pairs of electrons being shared between them, so there are going to be 3 lines. This is going to be a triple bond. This is a triple covalent bond. If there were 2 lines, it would be a double bond. If there were 1 line between these, it would be a single bond. So ultimately, what we have here is we have a nonmetal combined with a nonmetal. And together, they will give a molecule. Now, a molecule has covalent bonds. Electrons are shared. So think co-captain of a soccer team. Those captains share the captainship. So co means share, and then valent is referring to the valence electrons. These 2 nitrogen atoms are sharing these valence electrons, so this is a covalent bond holding them together. Ultimately, each of these nitrogens would have been pretty unstable on their own, but together they will have full octets, which is much more stable. So let's see what type of bond exists between the hydrogens and oxygens within water, and also whether that is a molecule or an ionic compound. So the first thing you want to think about is what type of elements are these? So hydrogen and oxygen are combining. Hydrogen is a nonmetal. Yes, the nonmetals are on the right side, and that is also nonmetal at the top left. And we also have oxygen, which is also a nonmetal. So hydrogen and oxygen and hydrogen are all going to be combining together. Hydrogen's electron configuration is 1s1. Each one will have one valence electron. And oxygen's electron configuration is 1s2, 2s2, 2p4. That will have 2 plus 4, 6 valence electrons. We know this because it's in group 6a. So recall, it's 8a in the noble gases, then 7a to the left of it, then 6a, then 5a, then 4a. So you can know the number of valence electrons just by seeing what group an element is in. So oxygen's in group 6a, it has 6 valence electrons. You can do that quickly, or you can write out the electron configuration and see there are 6 valence electrons. So writing out 6 dots. Now, none of these atoms on their own are stable. These are never found really in nature alone. Normally hydrogen is diatomic and oxygen is diatomic. They cannot be stable alone, and you can see that here. Don't have a full valence shell, don't have a full valence shell. But this oxygen here has 6 valence electrons. If it can get 2 more shared towards it, then it will soon become much more stable. It will have 8 valence electrons. And this hydrogen only has 1 valence electron, but in order to be stable, it only needs 2 valence electrons because if it ends in 1s2, then it will have the same electron configuration as helium, a noble gas. So this oxygen might share 1 electron towards it, and then another electron is shared towards that hydrogen. So soon we have the following. You can see that this right hydrogen has 2 valence electrons around it. Nice. That's the same as helium. And this hydrogen also now has 2 valence electrons around it. Very nice. The same as helium, the most nearby noble gas. And this oxygen now has 8 valence electrons around it, just like neon, the most nearby noble gas. So all of these now have full valence shells. This is very stable for all of them. So the Lewis dot structure of water then will have those two pairs of electrons still there, and then the electrons that are shared in between the atoms, those will be represented by lines. So like this is your final Lewis dot structure for water. Please note that most elements you're going to be dealing with need 8 valence electrons, like oxygen here. But hydrogen is an exception. It only needs 2 valence electrons to become stable. What that means is that hydrogen can only ever have just 1 line on it. So it can never be in the center. It always has to be on the outside.